Hello there and welcome to part 4 of Learn to Program with C. In this episode we're going to be talking about types and variables. But before we do that, there's a couple of housekeeping activities that we need to cover. The first is that for each of the episodes I've created a couple of files to help you. So if you look through the C files, it will give you, there'll be comments in there and it'll give you some examples around the topic that we're discussing. That's so I can keep each episode relatively short and not put all that in the episode. I'm also going to kind of put the exercise answers in there. The exercises are optional and you can do them if you want or not. It's useful, basically you've got to program if you want to learn to program. So you need to do something. So if you want to do the exercises, that's fine. So I'm going to put the answers to the exercises in there as well. And I'm going to put all this up on Git so that you can then clone this entire repository, and I'll keep adding to it with the episodes, and you'll be able to look at these extra files and see the answers to the exercises. So the Git repository is here, https://github.com. I can't fit this all on one line, but put this all on one line. /staropram, S-T-A-R-O-P-R-A-M. That's my ridiculous online moniker, which I just happened to pick up. Yes, it is based on the Staropram beer, or lager as it is. I happened to like that at the time. /C tutorial, C_tutorial. And to get this, you go to your terminal and do git space clone and then this. And that will clone a copy of it. And then you can also update this periodically. And I'll show you how to do that at the terminal in a video segment next. So in order to clone the repository, assume you want to clone it in a directory you've created called test. You do git clone, then the name of the repository, which is github.com/staropram /C_tutorial . That's actually it. This will then clone it, and that's done. If we then change into the directory and list the files, you can see the directories. I haven't actually put anything in here yet, I've just created this repository. If you then want to get the latest version of the repository, you don't have to clone it again, you can do git pull. And since it's already up to date, it says it's already up to date, but if it wasn't, it would pull in the latest changes. If you get like some major conflict when you try and do that, say for example you've been playing around with the files, just clone the repository again. Before we go on and look at types and variables, I just want to say a little bit more about the Printf function, because we're going to be using that. We used it in the Hello World and used it very trivially in the Hello World example. I just want to say a little bit more about it and how it works in general. So Printf, the F stands for formatted print, and inside the brackets it's a function, and we haven't covered functions yet, but we call a function by putting the open bracket and then its arguments and then a closed bracket. And the arguments to the printf function are a formatted string, so this will be our string here, and then within the string we can have format modifiers, which I'll explain in a second, and then we have the arguments to the format modifiers, so A, B, ... So that's the general format of printf. Now to explain what the string is and the format modifiers, we can't really do that without saying a little bit about types, which is obviously what we're going to cover here. But if the kind of exercise given at the last end of the Hello World one was to print the number 5 without just writing the number 5. So how we would actually do that is printf %d \new line and then the number 5. And what this does is the %d is what's called a format modifier. So this is our format string, and it's like a placeholder for the argument that comes after the format string. And d means decimal. So what this says is we want to print a decimal number. Here is the decimal number, it's the number 5, and printf will be called with these arguments, and it will mix these two together, and you will just print a 5 with it followed by a new line. So here's the program, our %d and then our argument 5. I'll just compile that and run it. There you go, it prints out 5. So that's the answer to the exercise. So just to say what Printf supports in terms of format modifiers, you've got %d for decimal numbers, you've got %f for floating point and double precision numbers, so like 3.14 or whatever. You've got %s if you want to print another string, so you might do printf s space %s, and then you could actually have 2 more strings in there. I can't fit them on there, but let's just say it was A and B. Then this would actually just print A space B. So there's a lot of examples of that in the Git repository, but the main ones we're going to be using in Printf are the %d and the %f options. So to show you those examples, if I want a decimal number, I use the modifier %d, and then I put the number in there, so 55. And if I want a floating point number, I use the modifier f, and there we go, I'll put a number in. If we just compile that and run it, you can see that the decimal number has been printed and our floating point number has been printed. And just to quickly show you another thing, we can print multiple numbers. So let's print 3 floating point numbers. We'll just print the same number 3 times. Actually, that's a bit silly, isn't it? We'll print 3 different numbers so you can see it. Compile it and run it, and there's our 3 numbers. And I'll just add one extra thing about printf. For a floating point number, if you want to specify the precision, after the % modifier you can do a decimal point and then the number of digits that you want to print it to. So if we print that to 2 digits, that to 3 digits, and that to 4 digits, and compile that and run it, you can see that that's to 2 digits, that's to 3 digits, and that's to 4 digits. Now we're ready to talk about types and variables, and we're going to start with types. In the example that you just saw, we used 2 different types. We used an integer type in printf, and we had to use the modifier %d, and then we passed in an integer type and printed that out. We also used a floating point type, and we used a modifier %f, and we passed in a floating point number and printed that out. So there's an example where C uses types. C supports many other different types. It might not be clear why we need types yet, but I'm going to start by just explaining what types C supports. And then once you've got an understanding of the range of types it supports, I'll explain why they're needed, what problems they help solve, and relate them to untyped languages. Some languages don't have types. The first type in C is char, which means character, because traditionally characters were single bytes. So it's not surprising then that a char is a single byte. It can, in this form, also store numbers. So it is 8 bits long, and it can store numbers in there in a binary representation. It can store the numbers from -128 to 127. Now you might be wondering, if you've watched my binary numbers tutorial, why we've got negative numbers here. Now this is because with binary numbers you can represent negative and positive numbers, And they do this by using the first bit, the leftmost bit, as a sign bit, so it indicates whether it's negative or positive. But by doing that, it halves the space for either positive or negative range. It's a bit like having a ruler. This one's 20 centimeters long, so I've only got 20 centimeters of space, but I could decide that the point at 10 centimeters is 0, and then I could measure -10 and +10 on the same ruler. But what we can do in C, we can have either a char, which is what's called a signed type, it goes from minus to positive, or we can have an unsigned char. And the range of an unsigned char goes from 0 to 255. Now if you count this up, you'll calculate that there's 256 different values that they both support, because it's the same space. So they're the first two values. So they're the first two types. Char is often used as well to store an ASCII character. So the ASCII character set was one of the first character sets that existed, and it's all 8-bit. So A, B, C, these are all character types. So to give a quick example of how this works, I can actually, using printf, there's a modifier to print a character, which is %C. And if I put A in there, then just compile it and run it, it prints A. Now, if I bring up a manual page called man ASCII, I can see the ASCII character set. And because the ASCII set fits its characters into a byte, there is a correspondence between values that are stored in a char and actual characters that we're familiar with. And in the ASCII man page, this correspondence is demonstrated, so that the number A is actually the number 97. Sorry, not the number A. The letter A, or the character A, is the number 97. And I can do that in the program as well. So if I put the number 95 there, compile it again, and run test. Sorry, I said it was 97, didn't I? I don't know why I did that, but just to show you there that it really is outputting the right character. There you go. So 97 is A. And so you can actually do that with types, with character types. And we could write ABC by putting 97, 98 and 99. Just put that in there. I'll put our 3 characters in a row. Compile that and run it. There you go, ABC. So there's a direct correspondence between the number stored in a character type and an actual ASCII character. So let me continue with types, and we'll go on to the next type. The next type is called a short. Now this has to be a minimum of 16 bits according to the specification. On my machine it is 16 bits, and on most machines it is 16 bits. A short can represent a number between -32768 and +32767, which is the 16-bit space. And like a char, you can have an unsigned short. So we can reuse the space. Which means that signed bit in the short will be used to increase the range of numbers we can store, which allows us to store between 0 and 65535. So that's the short. Now nobody really uses shorts anymore. You hardly ever see them. And in fact, it's very rare to see someone using a char to store numbers rather than characters. The only time you'll probably see this, and if you do go into this space then you'll see this a lot more often, is in embedded programming, where space really matters. You may see people using a char to store integers, or you may see people using a short to store integers, just so they're using less bytes. So 16 bits is 2 bytes. Let's look at the next one. The next type is the int type, for integer. Now this is what you will use for integer numbers on a day-to-day basis. This is pretty much in every program. If someone wants to use an integer, they'll use an int type. The largest size that an integer on your system can store will depend on the system and the compiler and library that you use. On my system, which is a 64-bit system, an int is actually 32 bits long and can store between -21474 83648 and plus 21474 83647. So you can see that with an int type you can store a very large range of numbers, and that's why you probably most of the time an integer is fine for what you're trying to do. Now an unsigned int can store between 0 and, wait for it, 429496. I've got to read it off here, it's so long. 7295. That's a pretty big number. That's up to 4 billion. But you can imagine if you're representing the Earth's population, that actually wouldn't be big enough. So you would need a bigger type. And there are bigger types. So what if I want to store more than 4 billion? Well, what I can use is a type called long. By the way, you'll sometimes see this written as long int. You don't have to put the int, but on a particular compiler you might need to put the int. Because a long keyword is actually a modifier of the int type. But on most compilers you can just put the word long, or you can put the word short. So, what can the long type store? Now this is so big, I'm not going to bore you with writing it out. As you can see, a long really is pretty long. And that is a very large number. So the chances of, I guess, you needing more than a long is quite remote. And you can have an unsigned long, which is just enormous for positive numbers. And believe it or not, there is another bigger integer type, which is long, long. So you'd write long, long to specify this type. And I'm not even going to write that out. Included in the Git repo, there's a program which prints out these numbers for you for each of the types, and you can then look at what a long long is on your system. But needless to say, it is a very big number. Alright, so that's integer types. Now let's look at floating point types. So now we're away from integer types and on to floating point types. So this is where we want to represent a number that has fractional components. So the smallest floating point type is called float. And on my system this is actually 32 bits. Originally, back when most computers were 32-bit, then this would have been 16 bits, but now it's 32 bits on my system. And in order to explain what numbers they can represent, first of all I'll just draw them out. Now what we have here is not a minimum and a maximum. What we actually have for each of these, this is actually plus or minus. So this is the largest magnitude number that it can represent, which is, if you remember scientific notation from school, 3.402823, and this e plus 38 means times 10 to the power 38. So that's a very large number. And that can either be positive or negative. So there's a sign bit in there. Now, what this top number is the smallest number that can be represented in magnitude. So magnitude means in the absence of sign, without sign. So in this, it's 1.175494 times 10 to the minus 38. So that's 1 over that number to the power 10 to the 38. So that's a very small number that's less than 1 and greater than 0. And we can represent that number either as positive or negative. So that's the kind of range of the floating point number. If we want to store a bigger number, then what we use is called a double. So, which stands for double precision floating point number. And just double. And double is the number that you'll probably always use if you want to. Double is the type that you'll probably always use if you want to represent a floating point number, because it's typically the size of your register on your machine. So I've got a 64-bit machine, and on my machine this type is a 64-bit type. So double can store very large and very small numbers. So what are they? So again, this is either plus or minus, and this is plus or minus. So the largest number will be 1.797693 times 10 to the 308, or essentially 2.225074e times 10 to the minus 308. So 1 over that. If it was raised to the power 308. So it's a very large range of numbers that a double can store. Again, there is even a bigger one which is called a long double, and that can store, bigger yet numbers than this can store. Now remember, with floating point numbers you always lose precision. They cannot represent all rational numbers, that's all fractions, precisely, because there's a limited number of bits. So you need to bear that in mind if you're doing scientific computing that requires high precision arithmetic, that any floating point number, besides what's called infinite precision arithmetic, and then it's only precise up to the number of digits you want, will lose precision. For most practical purposes this won't matter, but if you're learning this because you're going to do some scientific stuff, then you do need to understand what the limitations of these numbers are. Another type that's been quite recently introduced is bool. And this is to represent true and false values, and it can have the value true or false. In order to use this, you need to include the following header. It's called std bool, so standard bool.h. Now the reason that you have to include a header is because this is a new type, and they didn't want this name to clash with types in existing programs. So there is a non-clashing name, which is underscore capital B bool, if you want to use it. But otherwise include this header. So how were true and false represented before this type was introduced? Well, previously int was used for true and false. So, and how this was, a 0 equals false, and a 1 actually equals true. And in fact, if it's just not 0, so not 0 equals true. So 0 is the only integer that means false. Any other number equates to true in C. So you can see that that might be quite hard to understand what's going on if someone's using an integer to mean true and false. Most of the time it is pretty straightforward to see what's going on, but there are cases where maybe it's a bit elusive, and that's really why they introduced the bool type, to try and make it more readable. So we'll use the bool type, or we'll at least give some examples of the bool type in this tutorial, in these tutorials, because that's, going forward, that's I guess what people should be using. There are some other types in C. There is a complex type, which is in complex.h, which allows you to represent complex numbers. That was introduced very recently. And we won't talk about that now, but there are also some other types. There's a void type, which we're not going to talk about. There's also an enumerated type, which we're not going to talk about. And there's struct. The structure is probably one of the most important types, because it allows to build up kind of compound types from the basic types we've already looked at, like integers. Like say we wanted to represent a coordinate that had an x and y int, had one one int for the x position and one int for the y position, we could combine that in a struct and call that coordinate. Then we'd have a new type called coordinate type. So we can define our own types from the primitives, and that's what struct allows you to do. But we're not looking at that today. We're going to dedicate a tutorial to structs on their own. Okay, so at the very beginning of this I said it was about types and variables. But I also said in a previous video that I should try and keep the video short. I've been editing this and it's almost at 25 minutes now. So I'm going to talk about variables in the next video. So I'm just going to end this by cutting to a few programming examples about types, and then I'll see you in the next video for variables. So I've got the same layout as last episode with my two panes on the left and right. Now what I've done, I've downloaded the Git repository that I talk about at the start of this video, and I've gone into the 04 types directory. In there I can see 4 files at the moment, because I might have added more by the time this tutorial gets up there. But the ones in here at the moment are the exercise.c, which is we've seen already, which is the answer to the exercise from the last episode, and hellotypes.c. Now what hellotypes.c does is illustrate the use of printf for each of the types discussed in this episode. And so essentially all I do is print out a bunch of information, and in this case using the modifier %d for a character because it's I want to print it as an integer. And what I'm using, I included syslimits.h, which allows me to then use these macros here, schar_min and schar_max, which is assign character min, sign character max, and actually include the minimum and maximum values. And then I'm printing these for each of the types. So you can actually then see the limits for each of the types on your system. There's also some information in there about using the modifiers, the printf modifiers, to print integers and floating point numbers with different degrees of precision and padding. It's well worth compiling that and looking at the output very closely. I try and be quite verbose in the output, so you can understand how you can use printf to print out various different types, and also understand something about the types that are supported on C at the same time. To compile both those programs, just type make. What I've done, I've created a file called makefile, and this is a very simple makefile that just has the names of the two programs. You don't need to know how makefile works at the moment, and that will be a separate episode quite far in the future actually. But if you do want to add your own program in here, you would just add in my program here without the .c, and it would also compile that. And the advantage of using a makefile is that it won't recompile once it's done. So once it's compiled it'll only recompile once the file changes. So if I go in and edit hellotypes.c and even just add a new line and then type make, it will recompile hellotypes.c. So that's quite useful. But anyway, compile both programs by typing make, and then you can run hellotypes and pipe it through less. So what I did there, I used a pipe symbol and then less. So this allows you to view the output at a page at a time, and you'll be able to just scroll down with the arrow keys or the Vim keys and view the output there. And I would seriously recommend reading through that very carefully to understand all of the different types in C. Okay, well that's it for now. I would say as the exercise for the next lesson is try and print out a floating point number but using the printf modifier for an integer and see what happens. So do something like this, printf .d / and then a floating point number. Obviously do that in your C program, not on the command prompt. And see what happens, and try that for various different things and just find out what happens, and we'll look at that in the next episode when we're looking at variables. Okay, well that's it for now. Hopefully you've learned something about types. Next episode we're going to look at variables, and types are kind of useless without variables. So we'll see you in the next episode.